A mountain valley can look permanent. Sheer walls, a broad floor, a lake reflecting the peaks. If you enjoy surprising facts explained clearly, subscribe to Dr. No for a new discovery every day. But much of that scenery is not simply old. A glacier begins with an imbalance between snow arriving and snow leaving. Over many years, that imbalance can create a moving mass of ice powerful enough to redraw an entire mountain range. Look at a dramatic valley in places such as Alaska, the Canadian Rockies, Patagonia, or the Sierra Nevada. If its floor is wide, its walls rise steeply, and waterfalls spill from valleys perched high above it, you may be looking at the aftermath of ice. The glacier may be smaller now or gone entirely, yet its work remains written across the rock. The story starts high in the mountains, where winter snow survives the summer. Snowfall must repeatedly exceed melting, evaporation, and other losses. Each fresh storm buries the snow beneath it. Under the growing weight, delicate snowflakes lose their original shapes. Air is squeezed from the spaces between grains, and buried snow changes into dense glacial ice through an intermediate, granular stage called firn. This does not happen after one blizzard. It is a long process of accumulation and compression. Once enough ice gathers on a slope, gravity turns that stored ice into motion. A glacier may appear solid and still from a distance, but it flows slowly downhill. The ice within it deforms under stress, with layers and crystals shifting past one another. In many glaciers, water at the base can assist movement by reducing friction between the ice and the ground. That motion is the key. A glacier is not merely frozen water sitting on a mountain. It is a conveyor belt of ice, rock, and sediment. Along valley walls, falling stones land on the ice. Beneath the glacier, rock fragments frozen into basal ice become cutting tools. As the glacier moves, it presses that debris against the bedrock below. One process is abrasion. It scratches, grooves, and polishes bedrock as rock-laden ice slides across it. Fine particles can smooth a surface. Larger stones can score long lines called striations. These marks are useful clues. They can preserve the direction in which the ice once moved, even after the glacier has vanished. The second process is plucking. Here, plucking removes blocks rather than dust. Water can enter cracks in the bedrock beneath or beside the glacier. Where conditions allow freezing, the ice can bond to fractured rock. As the glacier continues downhill, the ice exploits those weaknesses and can pull away pieces of the bedrock. Those blocks are then carried onward, ready to grind more rock farther down the valley. Abrasion and plucking work together, but they do not act on a blank canvas. Before the ice arrives, running water commonly begins the excavation. A river valley starts as a V because flowing water concentrates its erosion near the channel at the bottom. Then a glacier occupies the entire valley. Ice touches the floor and pushes against both walls, widening, deepening, and smoothing the original river-cut shape. Over long periods, the valley becomes a trough with a broad floor and steep sides, the classic U-shaped valley. This shape is one of the clearest signatures of mountain glaciation. It is not a perfect letter U everywhere because bedrock structure, slope, and the thickness of the ice all matter. Still, compared with a narrow river valley, the difference can be striking. Now imagine a smaller glacier flowing into a much larger one. The main glacier is thicker and generally has greater erosive power. The smaller tributary glaciers cannot cut their valleys down as deeply as the trunk glacier cuts the main valley. When the ice retreats, a hanging valley remains high above the main trough. Water draining from that suspended valley may fall over the edge as a waterfall, making a visible difference in erosional power. The head of a glacier leaves another unmistakable feature. Cirques are the mountain's ice quarries. Bowl-shaped hollows carved near a glacier's origin. They often have steep headwalls and a lip at their lower edge. After the ice melts, water can collect in the overdeepened basin, forming a small mountain lake called a tarn. Cirques also explain some of the sharpest scenery in glaciated ranges. Two cirques can gnaw toward one another from opposite sides of a ridge. As their backwalls retreat, the dividing rock narrows. Eventually, the resulting ridge is an arête, a sharp spine separating glacial valleys. Where several cirques erode a mountain from different directions, a horn can emerge, a steep, pyramidal peak left between them. These shapes look sudden and dramatic, but they are the slow result of many seasons of snow, ice movement, freezing water, and rock removal. Ice does not only carve. The glacier also writes with debris. Everything it carries must eventually be left somewhere. When ice melts, it releases a poorly sorted mixture of clay, sand, gravel, and boulders called till. A moraine is an ice-delivered ridge or mound of that debris. Lateral moraines form along a glacier's sides, where rockfall from valley walls accumulates. A terminal moraine forms near the glacier's furthest sustained advance, marking where the ice front once stood. Moraines are especially important because they turn a vanished glacier into evidence that can be mapped. A ridge of till across a valley can reveal the former reach of ice. Several ridges may record pauses or renewed advances during an overall retreat. The word retreat can be misleading. It does not mean ice flows backward uphill. It means melting and ice loss at the front exceed the forward delivery of ice from higher elevations. So the glacier's edge shifts uphill while the ice itself continues to flow downhill. Some transported boulders tell an even more direct story. An erratic is a rock carried by glacier ice and deposited in a place where its composition does not match the local bedrock. A granite boulder sitting on limestone, for example, can be a clue that a glacier brought it from far away. Ice has no need to sort its cargo by size, so it can move fine sediment and enormous blocks together. Then meltwater takes over the story. Water emerging from a glacier can carry and rework the sediment that ice has released. Unlike till, which is dumped directly by ice, meltwater deposits are commonly sorted by flowing water. Gravel may settle first, then sand, then finer material farther away. Beyond the glacier, these deposits can form broad outwash plains. That same runoff changes the color of rivers and lakes. Milky water carries rock flour, an extremely fine sediment made by glacial grinding. Suspended particles scatter light and can give glacial water its cloudy gray, turquoise, or blue-green appearance. The color is beautiful, but it is also evidence of active erosion happening upstream. Glaciers can deepen basins in valley floors, and those basins may later fill with water. They can leave chains of lakes, dam water behind moraines, or carve valleys deep enough for long lakes to occupy them after the ice is gone. In coastal mountains, glacial valleys later flooded by the sea become fjords. The same basic forces of moving ice, bedrock erosion, and changing water levels can produce landscapes that look completely different today. The landscape becomes a record if you know how to read it. A U-shaped valley points to ice filling a former drainage route. Striations show movement. A hanging valley shows unequal erosion. Cirques, arêtes, and horns reveal ice working from high mountain hollows. Moraines and erratics reveal transport and deposition. Outwash plains and cloudy streams show what meltwater did next. This is why glaciers matter even where no glacier remains. They are not just features of cold places. They are former architects of terrain, capable of turning river valleys into broad troughs, ridges into knife edges, and mountain basins into lakes. The next time a valley seems too wide for its river, look beyond the water. The scale of the landscape may belong to ice,